I'm gonna give it just one more minute. I'm just trying to coordinate something here. It's not working for some reason. Alrighty, let's get started. Hope everybody's doing okay. I was trying to get something to work, but it wasn't. We're gonna get into the heart of all the differentiation applications today. We're gonna do some acceleration, we're gonna do some velocity, we're gonna do some related rates, some first derivative and second derivative tests. And I did my best to try to pick problems that I thought could show up on this test. Remember that the test that you're taking is not going to be a lot of computations. It's going to be more conceptual things. So keep that in mind as we go through some of the different exercises today. First off, we have a pop quiz, stuff that we went over last time. Let me set up the poll. So which of the following are acceptable phrases to mean f prime of c? We have 7 different options. Some of them are true, some of them are false. I'll let you choose. And then we also have what conditions need to be satisfied in order for the mean value theorem to apply. There's one more down there. Let's see. Hopefully you can see all of them. And then I'll give you a second to choose which ones you think are true. Go ahead and click the ones that you think are true. It's okay if you get some wrong. That's why I'm here, to help you explain. I'll give you a few more seconds. 5, 4, 3, 2, 1. Okay, so these are the results. So a couple things to think of when you get f prime of 3, right? I automatically think IROC, the instantaneous rate of change. So number 5 is true. The slope of the tangent line when x is equal to c. That is also true, right? it's not the average rate of change. Average rate of change is the same as the slope of the secant line, is the same as the point of continuity. And then this is, sorry, is not the same as the point of continuity. It's the same as number 6, right? 6 is another way of saying average rate of change. So it's just number 4, number 5 for part number 1. And for the mean value theorem to be applicable, the function must be continuous on the closed interval, and the function must be differentiable on the open interval. Okay, those are the two conditions that need to be satisfied. Alrighty, let's go on to some of the topics of today then. So first things first, these are all the topics that we'll be covering, at least for Unit 4, interpreting the meaning of derivative in context. We're going to look at straight line motion, rates of change, related rates, tangent line. We'll do a little bit of L'Hopital. Going to ask you for number 1 first. So C of 20 is equal to 140. So it says the function C of x, excuse me, gives the cost of digging a hole x feet deep. So what does C of 20 equals 140 mean? Does it mean that a hole 140 feet deep costs $20 to dig? A hole 20 feet deep costs $140 to dig? And then what does C prime of 20 mean? C prime of 20 equals 5. Does that mean that the hole, when the hole is 20 feet, the cost of digging is increasing at the rate of 5 feet per dollar? Does it mean that when the hole is 20 feet, the cost of digging is increasing at a rate of $5 per foot? Or when the hole is 5 feet, is the cost of digging increasing at a rate of 20 feet per dollar? So make sure, share these results with you. I think most of you got these right. Remember, when you're interpreting, to keep straight the units. So the input is 20 and it says it's 20 feet. So that means a hole that's 20 feet deep costs $140 to dig. And then this 20 is that when the hole is 20 feet, the cost of digging is increasing because it's a positive number at a rate of 5. And then think in your head dy dx, right? dy is the change in y, so $5 per foot. Your dx is feet. Cool. Alrighty, so then we move on to section 2, which has particular motion. So what's the order of things as we go? So if we have the particle's position s of t, that means s prime of t must be the derivative, which is also known as the velocity function. And so if we take the derivative there, remember tans are sexy. So 1/2 secant squared of t. Well, that's our velocity function. And then we can do s double prime of t is equal to your acceleration function. Ooh, how the heck do we take the derivative here? So we do 1/2 power rule, 2 secant of t. Or then chain rule. Chain rule is the derivative of secant is secant t tangent t. And then what do? We go ahead and plug in pi of 6. Does anybody remember what secant of pi over 6 is? Fortunately for you, you actually don't need to remember. Like if you were to just put this on the test, you get full credit. But secant is a reciprocal of cosine, right? And cosine of pi over 6 is rad 3 over 2. So if you want to evaluate, it's 2 over root 3 squared. This 1/2 and the 2 cancel. And tangent of pi over 6? Tangent pi over 6 is rad 3 over 3. And can somebody tell me, type in the chat box, what the units of measure would be for this acceleration function? Minutes per feet squared? Not quite. So remember that your distance is feet, right? When you take the derivative, it's with respect to time. So for velocity, it would be feet per minute. And then when you do it again, it'd be feet per minute squared. And we could keep going, right? Every time you do it again, you take another. So the third derivative, also known as the jerk, would be feet per minute cubed, and feet per minute to the fourth, right? And it's not seconds, be careful, because it said in the question, it's in minutes. So just little things to keep track of. Alrighty, so then we have 4.3. 4.3 is just a little bit more conceptual. One of the equations there is representing linear growth, and then one of the equations down there is representing exponential growth. This poll to test you here to see. So let's call this one A, let's call this one B, let's call this one C, let's call this one D, let's call this one E. Like, which one do you think is a linear growth? Choose A, B, C, D, or E. And then which one do you think describes exponential growth? I see. I see, I see, I see. So notice that on this one, it's given in terms of the rate. And remember, another way of saying linear growth is constant rate of change. When you have linear growth, you have a constant rate of change. And in which one is the rate constant? It's actually A. A is the linear growth function. A lot of y'all chose B because you're thinking, oh, a linear function. But these aren't linear functions. These are in terms of the rate. So the first one is linear rate. And then when you're doing exponential growth, it'll be D. D represents exponential growth. There's a huge reason when we get to differential equations. But just commit this to memory for now if you need to see this. It's a dp and then p. So you have the same y variable on both sides. The rate of change with respect to y is something times that y value. Any questions so far? Okay, so we did a lot of 4.4 yesterday, so that's why I crossed it out. That's just using implicit differentiation. 4.5, we're going to do a bunch of questions on 4.5 today because those are, I think, the most relevant for free response questions out of this unit. How about 4.6 though? So get your thinking caps on, see if you can type in the equation for the tangent line. So I want the tangent line equation. Okay, we're given this point here, g of -3 is equal to 2, and we're given g prime of 3 is equal to 7. So don't plug in a number, just give me, in your question, don't use F. G of x equals something, so you can practice typing this out in case you plan to type it. What does g of x equal if I want my tangent line equation? Cool, good job, Alita. So I'm gonna write the equation in Taylor form, right? So when I have Taylor form, I'm gonna put the y point first, so my y point of my function is 2, right? And then the next one is my slope. My slope goes second. My slope is 7 at that point, and then it'll be x minus my x coordinate, so it'd be x plus 3. That's just how I prefer to write my equation, but any variation of this would be correct as well. And then if you need to approximate your tangent line, you're just going to go ahead and plug in negative 2.9 for x, right? So you get 2 plus 7, negative 2.9 plus 3, and then that's equal to 2.7. And then, of course, if you want to have completely proper expressions and equations, you could write something like that. Right, so that's a review of all the major concepts from Unit 4. So now we get to some of these tricky related rates questions. So I think the tricky part is, number one, you have to pay attention to the wording, and number two, you have to pay attention to the units that they're talking about too. So I feel like I said the same thing twice. Pay attention to the wording, pay attention to the units, pay attention to the implicit differentiation. That was the second point I wanted to make. Okay, so the first one, what do they give us? They give us a cylindrical barrel. It has a diameter of 2. So right off the bat, they already give something that could trick you, right? When they give you diameter, usually they want radius. And it says the water drains out through a valve not shown at the bottom of the barrel. The rate of change of height with respect to time. So this is dH dt, right? So you're lucky that they gave it to you, but this sentence translates into that phrase. And it's given with that equation there where h is measured in feet and t is measured in seconds. And they're also nice in that they gave you the volume of a cylinder. Why somebody's calling. Find the rate of change of the volume of the water of the barrel, right? When they want the rate of change of the water in the barrel, they want dV dt, right? So how do we find dV dt? Well, let's start with V, right? So dV dt is the derivative of pi r squared h. How the heck do we take this? Well, pi is a constant, right? We can factor out that constant because constants don't matter. And then here, what do we get? We have to do a product rule. First times derivative of second plus second times the derivative of the first. And I'm thinking if y'all want to try to write something like this, I bet they'd have a pi symbol or something. You could also type it out as pi is equal to r squared h prime maybe, plus 2r h times r prime. Maybe that'd be a way you could write this. What do we know? We know our h prime, right? They give us our h prime, but I'm stuck with this r prime thing. I'm gonna write in the h prime. Can somebody tell me what r prime might be? Anybody? So let's think what r prime represents. Yes, Christopher got it right. R prime is the rate of change of the radius. And if we look at the picture right here, what's happening to the radius? The radius isn't increasing, the radius isn't decreasing, the radius is staying exactly the same. So in this problem, if you want to plug in for dr dt or r prime, they're both equal to 0. So this entire right-hand part completely cancels out. So that's nice. And then we can go ahead and plug in the numbers that we're given, right? We know that our radius is 1. So we plug in for 1. So pi times 1 squared. And then we know that our height is 4. So it's 1 squared times negative, square root of 4 is 2. I'll just write square root of 4 though, over 10. And then what are our units of measure? It's the rate of change of volume with respect to time. Volume is in cubic units, so it's cubic feet per second. Did I get the time right? Yes, seconds. Always double check, right? So this would be an acceptable answer for the test this year. Any questions on that one? All right, part 2. It says when the height of water is 3 feet, is the rate of change of height of water with respect to time increasing or decreasing? And then the ominous words of explain your reasoning. So let me show you the wrong way to do this. The wrong way to do this is just to plug in 3 into this and call it a day. Okay, that is absolutely the wrong way of doing it. Why? Let's pay attention to the wording of this question. It says when the height of the water is 3 feet, is the rate of change, is dH dt increasing or decreasing? How do you find when dH dt is increasing or decreasing? You need to take the derivative of dH dt. Let me go ahead and change my pen color so when y'all look at the notes, you don't think I'm doing the same question twice. What color? Let's do blue. So then this, we need to take the derivative of both sides. So how do we take the derivative? We do this fancy symbol d dt of dH dt on the left-hand side. And then let's take the derivative of the right-hand side. It's -1/10, which is a constant. The derivative of rad h is 1/2 rad h. Since we're taking the derivative with respect to time, we need a dH dt there also. And then we kind of did something like this yesterday, right? When we had the dH dt, you got to make sure you substitute it back in. So let me simplify the first part is 1/20 rad h. And then what is dH dt? dH dt is that whole thing, -1/10 rad h. And guess what? The rad h's cancel out. Boom, boom. So then what's my second derivative? My second derivative is +1/200. And then on the right side, I can do d squared h over dt squared. So what does that tell me? When my second derivative is positive, is the rate of change increasing or decreasing? Well, since the second derivative is the derivative of the first derivative and it's positive, my rate is increasing. And then your explanation could be something along the lines of, because d squared h over dt squared is greater than 0 for all values of t. Right, it doesn't matter what your t value is, right? It's always going to be +1/200. You can say dH dt increases for all values of t, something like that. Any questions on that one? All right, part 2. This was on the exam 2 years ago on the both the AB and the BC exam. So we're given this function, the height of the tree, where x is the diameter of the base in meters. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. So then we can call this what? It says x is the diameter, right? So then this is dx dt. According to the model, what is the rate of change of the height with respect to time? So let's take the derivative of both sides. So g prime of x is equal to, we have a quotient here. Low d high minus high d low, derivative of 1 plus x is x, all over square of what's below. Is everybody satisfied with how I took the derivative? No complaints? So you got to remember that when you're doing the derivative, you're taking the derivative with respect to time, right? So I had to do dt of g of x, right? If I'm taking the derivative with respect to t, you need this dx dt part. Or it could have been incorporated while you're doing it, right? So let me change this. Like, for example, when I did the first part, it's first. I apologize for all these people calling me. I guess I'm really popular today. It's first times the bottom times the derivative of the top, right? So you could have put dx dt here, right? And then top times the derivative of the bottom, so you could have times it by dx dt there also. So please do not forget to do the derivative with respect to t. Do the implicit differentiation part when you're doing this problem. Right, and then from there, you can just go ahead and plug in the values, right? So every time you see a dx dt, you plug in a 0.03. Anytime you see an x, you plug in 50. Any questions on this one? I'll just go ahead and plug in the values then for you, just so you can see them. Ooh, the other thing you want to pay attention to, it says increasing, right? So I should have, they like to trick you sometimes and say decreasing. So make sure you pay attention to your sign there. Minus 100 times 50 times 1 dx dt 0.03. All of this over 1 plus 50 squared. And then what should my units be? Rate of change of the height. So height is in meters per year. So meters per year. Any questions on that one? Alrighty, let's move on to this one. At time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius when time is equal to 0, and the internal temperature of the potato is greater than 27 degrees Celsius for all times t is greater than 0. And then they give you this equation for the potato, and then give you that h of t is measured in Celsius and h of 0 is equal to 91. Write an equation for the line tangent of the potato. So I'll let you try to do this. Take a couple minutes and see if you can figure out the tangent line equation for the potato. Why anybody would take a potato off the stove and leave it to cool is kind of beyond me. We don't want t equals 3. So when t is equal to 0, h is equal to 91, right? I think that's something to think about there. So then you're going to plug in dh dt, negative 1/4, 91 minus 27. 91 minus 27, 64, right? Negative 1/4 times 64. Negative 16. Remember that dHdt is the slope of your tangent line. So then from there, you can just write the equation of the line, right? So we get h of t is equal to, what's our starting point? Our starting point is 91. 91 minus the slope, and then I'll do x minus there just to be a little bit redundant right there, right? So that is the equation of your tangent line. And then from there, you can just plug in 3 to evaluate what the approximation is here, right? So if you were to write this on the test, make sure you put your squigglies because this is an approximation, not an actual value. (91 minus 48) is 43. Cool, so that's a tangent line approximation that could easily show up. And then what about part B? It says take the derivative with respect to both sides. So take a second and see if you can help me calculate d squared h over dt squared. See what you get for part B. So a couple things you can do here, right? You can distribute if you want. Good. Good. Yeah, Alita, you got the right answer. What'd you get for the second derivative though? Right, so we're going to take the derivative with respect to t of both sides. Right, so d squared h over dt squared, right, is equal to negative 1/4 dh dt. The constant goes away when you take the derivative. Right, and then we plug in that dh dt, right? So negative 1/4 times another negative 1/4 h minus 27. Right, so this is equal to positive 1/16 at h minus 27. That's my second derivative differential equation. And then what? Use your answer in part A. What did we know? We found that h was 43 in part A, right? And we go here and plug it in. When we plug in 43, we get it's concave up, right? The second derivative is positive. So how would you justify this? You could say, well, let me give you a picture first for those of you who aren't sure. Let's say we have a graph, right? We know the graph is concave up, right? So that'd be looking something like that. Oh, it should be decreasing. Sorry, it's a cooling potato. So this is a concave up graph, right? And then when you have the slope of the tangent line, this is your tangent line right there, right? And if you're approximating the tangent line, the point that we picked was right there, but the actual value is a little bit above. So whenever you have a concave up function, whenever d squared h over dt squared is greater than 0, your function, your tangent line is an underestimate. Any questions there? This one's easy. I'll post it on the notes, and if you want to try it, you can try to do it. But I think all the other ones are a little bit more conceptual than this one. I do want to go over this one though. So what's going on here? They give you this train A, and it runs back and forth on an east-west section of railroad track. And then they give you the velocities. So remember that the velocity is the first derivative. And then in part C, they say a second train travels north from the origin station. So let me go ahead and draw a picture over here. So train B is traveling north from the origin station, and time t, the velocity of train B is given by this equation over here. And then when time is t is equal to 2, the train is 400 meters north of the station. So then this is where train B is. From an earlier part of the question, they also told us that the position of train A when t is equal to 2 was 300 meters to the east. Okay, so train A is over here. And this is 300 meters. And now they're saying find the rate in meters per minute at which the distance between A and B is changing at time t equals 2. So the distance is this thingy right there. Let's use C. So when you're doing related rates equations, you want to think about setting up an equation. What's the easiest equation for us to use here? Well, by drawing it out, I hope you can see. A squared plus B squared is equal to C squared. All right, so we're just going to take the derivative with respect to time of our Pythagorean theorem. Right, so when we take the derivative, what do we get? We get 2a, a prime, plus 2b, b prime, plus 2c, c prime. So remember, don't plug in anything until after you've taken the derivative with respect to time. Otherwise, you're going to get into a world of hurt and you're going to get things canceling out like crazy. So now we can plug in the values. So what do we know? We know that the position of A is 300. We need to find the A prime, which is the velocity of A when t is equal to 2. It's given to us in the table. All right, so that's 100. What about B? So B is 400 meters north. And then what's the velocity? Well, we have to use the velocity equation. So we'll do what? -5 times 2 squared plus 60 times 2 plus 25. Right? All of that is equal to c squared, or 2c c prime, excuse me. And what's so nice about this picture? Well, when you know that one of the legs is 300 and one of the legs is 400, then automatically the hypotenuse is 500, right? It's 2 times 500 times c prime. And what are we solving for? We're solving for c prime. So all we need to do is simplify this whole thing on the left-hand side and divide over. So this whole thing on the left-hand side is equal to 80,000. And then we're going to divide it by 1,000 is equal to c prime. And then what are our units here? Meters per, what is t? Minutes, meters per minute. Who has questions on related rates? I tried to pick the ones that I think were most likely candidates in case you're to see a related rates question. Okay. This one I wanted next. Yeah, okay. Extrema on an interval, right? Extrema is just a fancy way of saying maximum or minimum. And I just want to go over this really quickly just to show you the different ways there are of calculating extrema. So thing number one, we have this extreme value theorem. You don't actually need to know it, but you will need to evoke it quite often, right? If f is continuous on the closed interval a to b, then there must be both a maximum and a minimum value on that interval. It could be the same value, right? You could have a horizontal line and it still be the maximum and the minimum. So just something to think of though is like when you have some sort of discontinuity, then this theorem no longer applies, right? Here we no longer have a max value in A. Same with B, right? Infinity is not technically a number, so the max value does not exist. Okay, so that's part one. Okay, part two, critical values. I want to go over this really quickly. I know you're all familiar with it, but I think the thing that people forget is when you take the derivative, sometimes you need to set the derivative into does not exist. So not only do you get critical values when your derivative equals 0, you also get critical values when your first derivative does not exist. Another theorem to think about, extrema can only occur at critical values or the endpoint of an interval. Whereas underneath, relative or local extrema can only occur on the open interval, so not the endpoints. So we have absolute versus relative. The absolute maxes and mins, you should test your endpoints. For relative, you do not need to test your endpoints. Okay, so look at the notes. This is not to say that there is extrema at every critical value. Right? For example, you could have the cubic function, right? If you were to take the derivative of the cubic function, you'd find that this is a critical value, but that's not a max or min, that's actually a point of inflection. But remember that critical values can represent maxes, can represent mins. And then just remember that relative and local extrema cannot occur at the endpoint of an interval. Cool, so then the next thing I want to do is I want to walk you through the best optimizations that I could think of that might show up and talk about justifying. I think it's going to be more important that you know how to justify these things. So when you're finding absolute extrema, here's what you need to do. You identify the endpoints, identify the critical values, and then you find the function values. So usually you can just make a table, and that table is enough justification for you to show that something is an absolute max or an absolute min. Okay, and then answer the question in a complete sentence because they care about complete sentences on the calc exam. Right, so keep that in mind. This is one of those things that maybe it makes sense for you to write out, to copy paste it, do whatever, so you have this, because I feel like this is a very likely candidate for a question. I'm not gonna read this whole thing to you, but do note that I have these notes here for setting up a successful optimization problem. And then there's also 2 other ways to justify absolute extrema. And I picked 3 problems so we could see one of each way. Alrighty. So number 13, find an equation in general form for the tangent line of that having maximum slope. So let's find the slope equation then, right? So if we know that f prime is that, let's find, or f is that, excuse me, let's find f prime. Or what's f prime? This is gone, right? It's 0, minus 2, minus 2x, minus 3 times 1/3 is 1, x squared. So this is my slope equation. Reorder to make it look prettier. But now we want to maximize that equation. Okay, so if we want to maximize our slope, aka f prime of x, what do we need to do? We need to take another derivative. So negative 2x minus 2. Now we can set it equal to 0 undefined. Obviously, it's a line, so it's not going to be undefined. So we set it equal to 0. What do we get? We get negative 2x is equal to 2, x is equal to negative 1. Right, but you can't just stop there. We need to show that it's a maximum. How do we show that it's a maximum? We can do a number line test on this one, actually. Now, yes, good. So remember that drawing a number line is not going to count. So in previous versions of the exam, if you drew a number line, they can't look at any of your pictures. The pictures are solely for you. So if we plug in negative 1 into my first derivative, I see that I would get negative 2 times negative 1 is 2. Oh, sorry, I need to plug a bigger negative number. Let's try negative 10. Right, so then I get 20 minus 2. 20 minus 2 is positive. Right, and then I'll plug in positive 10 here. When I plug in positive 10, I get negative 20 minus 2. So I get that this interval is negative, right? So this is increasing and this is decreasing. So this is where you can evoke method 2 because we don't have endpoints to test, right? This is an unbounded interval. We have negative infinity to positive infinity. So you could say something like, because f double prime of x is greater than 0, that's how you write positive, right? For all x is less than negative 1, right? And f double prime of x is negative for all x is greater than negative 1. There is an absolute max value for f prime of x when x is equal to negative 1. That would be a proper justification statement if you didn't have endpoints to test for a maximum. Cool. Now we need to find the tangent line. Well, we know our value now. So what do we need? We need a slope. How do we find a slope? We have to use our first derivative. So what is f prime of negative 1? Negative 1 squared is 1. Negative 1 minus 2 times negative 1 plus 2 minus 2. My slope is negative 1. That's my max slope. And then what do we also need? We need a value of the function, right? So we need an f of negative 1 also. Oh, this is gnarly looking. 2/3. What is that? Plus a 2 minus a 1 minus a 1/3. Am I right? I think I'm right. Plus a 1/3. That makes it better. Oh, phew. Thought we're gonna have to deal with fractions. So 2/3 plus 1/3 is 1. 1 minus 1, 2. I found my point. F of negative 1 is equal to 2. All right, so then we can just write out our tangent line. F of x is equal to 2 minus 1, x plus 1. Questions on that one? So make sure you pay attention to the justification part. That's where I would assume all the points are going to come from on the test this year. Justification. So we've justified one using unbounded intervals. Let's do one using a bounded interval. So a rectangle has its vertices on the x-axis, the y-axis, and the origin in the graph of 4 minus x squared in the first quadrant. So this question was kind of mean in that they didn't give you any pictures, but obviously if you want, right, you can use Desmos, get a picture, probably switch up a color. You probably are all sick of my color right now. We're bounded in the first interval, right? So first quadrant, so we have this bounding right there, right? And you have this point over here. Oh, I'm using Barney colors. All right, we're trying to maximize this rectangle over there. Well, what's the area of such a rectangle? The area of such a rectangle is just what? Base times height. Right, the base is x, the height is y. Right? So normally with these optimization questions, we need a secondary equation. Does anybody know the secondary equation we need to use? I can't take the derivative with respect to two variables on an optimization question. Anybody? When they give you the equation of the graph, if you know the equation of your graph, you can just use that as your secondary equation to plug in. Right, so now A with respect to x can just be written as x times 4 minus x squared. Expand, so I don't have to do the product rule, because I don't like the product rule. Now we can take the derivative. A prime of x is equal to 4 minus 3x squared. Critical numbers, right? We set our derivative equal to 0 undefined. So we get what? We get x squared is equal to 4 over 3. Right, and then x is equal to plus or minus square root of 4 is 2. Square root of 3 is root 3. Right, we get two values. However, we can toss out the negative one, right? Because we're only in the first quadrant. Negative, go away. Okay, so similarly here, if you want, we can do a number line test. Except what's going on? We actually know that there's a bounding here, right? There's a bounding on the left-hand side, so we can actually bound it at 0. And technically there's a bounding on the right-hand side also, right? We can't go past this point, otherwise we're gonna end up in quadrant 4. And if you see this and you set this equal to 0, this point of intersection right there is just 2. So we can actually use bounding over here to figure this out. And then I'm going to evoke the second derivative as a justification. So let's take the second derivative of our area function. The second derivative of our area function, the 4 goes away. So we just get negative 6x. And what's the deal with negative 6x? Well, we can do a number line with that one too, right? We can find the critical value there. And then, so x is just equal to 0. Well, what happens for the second derivative when x is greater than 0? We know that because we're in the first quadrant, right? A double prime of x is going to be less than 0, right? Because a double prime of x is a negative 6x. So anytime I plug in a positive x value, I'm going to get a negative second derivative. If I get a negative second derivative, that means my thing is concave down. And when you have a concave down function, then 2 over root 3 is a max value for a of x. That's evoking the second derivative justification. Any questions on that one? Obviously, the question's asking for possible area. So then the last final step, you want to do a of 2 over root 3 and plug that in. I'll just leave it there. I'm just focusing more on the justification. Alrighty. The last one that I think could show up for optimization, I want to make sure y'all are ready for this, is trying to find the point closest to the graph. Back to purple. Here's my graph. It goes to 0, 4. And then I gave you this value, right? This is 2, 0. This is 2, 0. Negative 2, 0, excuse me. And then they give you this point over here, which is 0, 2. And they want you to minimize, right? Closest is to find the minimal distance. So then plot a point then. Right, we don't know what that point is, so I'm going to call that xy. So they even tell us we want to minimize the distance, right? So we're just going to use the distance formula. What is this? D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And what are our 2 points? We have this one and this one, right? So we get x minus 0 squared plus y minus 2 squared. Again, what are we going to do with this y? We're going to yoink the y from here. And that gets yoinked and put in there. So the distance is equal to the square root of x squared plus parentheses 4 minus x squared minus 2, all of which squared. So let's simplify this a little bit. What do we get? We get x squared negative x squared. 4 minus 2 is 2. And then we get to here, we get x squared. And then this is what, x to the 4th. We FOIL minus 2x squared minus 2x squared plus 4. So then if I were to rewrite everything and simplify, it'd be x to the 4th. X squared minus 4x squared is negative 3x squared plus 4. Yay, we finally found our distance in terms of one variable. So this is where people get really, really stuck because they're like, okay, now I need to take the first derivative and set that equal to 0. But then I have this gnarly square root, and then I'm gonna have to do chain rule, and then I'm gonna have to do all these things, right? So the trick is when you get a max or minimizing a distance or maximizing a distance even, you can actually ignore the square root because the critical values without the square root will actually be the same with the square root. So we can say d prime then, and we're just going to take the derivative of the stuff under the square root. I'll put a note here for people who want to look at this later. We can ignore square root. Scroot for short. Okay, so the d prime would be 4x cubed minus 6x. And then we just need to maximize that. So d prime, we'll factor out a 2 and an x, and then what are we left with? We're left with 2x squared minus 3. We said each of these equal to 0, so x is equal to 0, and then x here is equal to plus or minus square root of 3 over 2. Now let me show you the last way we can justify it. We are given a bounded interval here. So when we're given a bounded interval, all we need to do is create a number line test or a t-chart, I guess. Okay, so we're gonna put in our x values here, and then we're gonna put in our distance here. Right, so what are our endpoints? I gave you the endpoints 0 and 2, and then we don't need the square root of negative square root of 3 over 2, right? So we just need to test the positive square root of 3 over 2. And then I'm gonna plug them into my distance equation. Make a note here, this is my distance equation. This is the one I'm plugging into there. So let's go ahead and plug. So what happens when we plug in there? We just get square root of 4, right? And I don't need to evaluate. The next one, you can use your calculator on here if you don't trust me, but the 4th power of the square root of 3 over 2 is 9 over 4. Plus 3 over 2 squared should be a minus. Times 3 is 9 over 2. Plus 4 is equal to the square root of 7 over 4. And then the last one we plug in 2. When you plug in 2, you get 8. And so you can say that this is your max value, right? And then this one's your min value. Any questions on that one? So just for a frame of reference, the t-chart or plugging in values are the easiest way of justifying. I got a question, why did I use 2 for the t-chart? I used 2 for the t-chart because my interval was bounded given at 0 and 2. And one of the ways of testing for absolute maxes and absolute mins is by plugging in all your critical values and your endpoints. Any other questions on this one? Okay. I will make sure to post all these notes in Dropbox so you can see all my scribbles. Okay. Gonna get the class involved a little bit again. So we're gonna do some graph analysis now. So for this graph analysis, we're asked about the mean value theorem. So my question to you is, how many values of x on the open interval, -4 to 4, satisfy the conclusion of the mean value theorem? Right, so just as a refresher, mean value theorem is if the function is continuous and differentiable, right? Then f of b minus f of a is equal to b minus a. We got differing results here. So what is f of b minus f of a? F of b minus f of a is the secant line from here to here, right? So how many points along the graph is the tangent line equal to the secant line, f prime of c, right? So 1 point over here, right? This tangent line works. This one here, right there. This one here, right there. So the answer is 3. There are 3 points at which the tangent line is equal to the secant line. Now we have this part. Now given g of x, the same function as above, x has intercepts at -3.8, -1, 0, and 3.4. Let me label that for you. That's 3.8, -1, 0, and 3.4. And the function has horizontal tangents. Let's use different pictures so it's easier to see, different colors, I mean. This, and this. -2.9, -0.5, and 2.2. So I'm going to ask you to put in your answers on what open interval. Oh, excuse me, let me say this. It says let h be a twice differentiable function such that h prime of x is equal to g. So this graph is the derivative of h. So given that this is a derivative graph, plug in your answers. Tell me what you think the intervals on which h is increasing. When is h increasing? You're right, but I want you to get an opportunity to write your intervals in case you plan to type it. I mean, you can also write it too. What intervals is H increasing on? So Alita came in and said whenever G is positive, right? Well, positive is when the graph is above the x-axis. When is the graph above the x-axis? Well, from -4, right, to -3.8. We cannot include 3.8, right? So we're going to use an open parentheses, union, open parentheses from -1 to 0, union 3.4 to 4. Actually, on the endpoints, I should also use open bound too, just because I don't know what happens right there. So an open boundary there and -4 there. All right, then obviously for part 2, when is h of x decreasing? It'd just be the exact opposite, right? So we go -3.8 to -1, union 0 to 3.4. Okay, so that one's pretty straightforward. If you know 1, then you know 2. Okay, next question on number 3. On -4 to 4, what are the x coordinates of each local relative max? Type in your answers, please. When are the coordinates of x at a local or relative max? Right, so whenever the function is going from increasing to decreasing, right? So whenever the function is going from positive to negative, right? So this answer would be when x is -3.8, right? Because the graph is above the x-axis before it, and when the x-axis, it's negative after it, and 0. And then what I want you to pay attention to is how you actually justify it if you get a question like this on the test, right? So you could say something like, because h prime of x changes from positive to negative at those values. Right, similarly, we can do the same thing with part 4. Okay, now part 5 then. On what open interval is h of x concave up? This one's a little bit harder. Plug in your answers. When is this graph concave up? So remember, concave up is when f double prime is positive. Right, and f double prime is positive when my f prime is increasing. When is f of x increasing? That's literally when it's sloping upwards, right? So it's sloping upwards from -2.9, right? That was the value they gave us. They said the horizontal tangent line was at -2.9 all the way to -0.5, right? And then we have another one at 2.2. And it's not going to be infinity. We're bounded here at 4. And actually, this thing that I wrote here, would be acceptable for justification, right? F double prime is positive when f of x is increasing, and that would be it. And you could do the same thing for part 6, right? So h double prime of x is negative when f of x is decreasing. Right, these are proper justifications. And then the x coordinates of each point of inflection. So remember, not only do you need to set your second derivative equal to 0, but you also need to check that it's changing signs. So tell me what the x coordinates are for each point of inflection on h of x. So if we follow the graph, right, it's decreasing until negative 2.9, but then it starts to increase, right? So we have an x coordinate at negative 2.9, that's a point of inflection, right? And then we have another one at negative 0.5, that's a point of inflection. And then we have another one at 2.2, right? Because every time the graph switches direction. Any questions on that one? Okay, so then how does this apply to an AP exam? Right, so this was from the 2015 AB exam. And it literally asks all these questions, and it gives you, the figure above shows you the first derivative of f on the interval negative 3 to 4. The graph has horizontal tangents at negative 1, positive 1, and positive 3. You don't need this next sentence. That's for a part that we're going to go over next time. Find out coordinates at which f has a relative maximum. Give me a reason for your answer. So take a second and think about how you would try to answer this if you were actually taking the test. So go ahead and type your answer into the chat box, please. And try typing in your explanation too, right? So they probably give you a point for your numbers and they'll give you a point for your explanation to see if that's a proper explanation. I think you gave me point of inflection. This one's asking for a relative maximum. Yeah, so what are you supposed to do? Like theoretically, if you were to get this question, you're supposed to identify all the critical values, right? So you start with f prime of x is equal to what? 0 when x is equal to negative 2, 1, and 4 maybe, right? Then you can do a number line test, right? Negative 1, negative 2, 1, and 4. 4 is the boundary, so you just don't need to go past that, nothing past there, right? Negative 2, it's above the x-axis, then it's below, and then it's below, right? So a short and concise answer would be x is equal to negative 2 because f prime of x changes from positive to negative when x is equal to 2. -2, right? That would be sufficient to get the point there. Part B, on what intervals are the graph both concave down and decreasing? Give a reason for your answer. So type in an interval into the chat box and then give a reason. So if I were doing this one, I'd kind of try to do a stacked number line test so I can kind of see both. So let's have this one be f prime of x, right? So we did that number line test, -2, 1, and 4. And then we can put -3 over here, right? And then what do we do? We did plus, minus, minus. And then underneath, we could do a second derivative number line. Right? Remember, the second derivative is where my first derivative is either increasing or decreasing. And it changes here at -1, right? So -1 would be over here. And then it changes again at +1, which is the same value right there. And then changes again at +3. And so let's evaluate the second derivative. We get the second derivative is decreasing because it's sloping downwards. It's increasing over here. It's decreasing again, and it's increasing again over here. And then with my number line, I can kind of like cross over and see which regions are going to work. Right, so this region was negative, and this region was negative. So I can split up into those subintervals. Right, we want concave down. That means we want f prime to be double prime to be negative. And then we want f prime to be negative. Right, so we're trying to find the entire regions where we have 2 minus signs. So this region right here works, and then this region right here works, right? This is the one that has the 2 negative signs. So the answer to part B would be between 2 and -1, and between 1 and 3. And then we can say, because f prime of x is less than 0, and f double prime of x is less than 0 along those intervals, or some variation of that. Alrighty, one more. Part C, it says find the x-coordinates of all points of inflection on the graph of f. Give a reason for your answer. So try typing in your explanation to see if you can get the point for that one too. So remember that the second derivative occurs when concavity changes. right? So if we were to recreate the number line from the previous part, right, we get -1, 1, 3, and 4. Concavity is negative along -3 to -1, right? Concavity is positive along -1 to 1. It's negative again from 1 to 3, and it's positive again from 3 to 4. So every time there's a change, so here there's a change, here there's a change, and here there's a change, right? So we have 3, 1, and 3, because you could say something along the lines of f double prime of x changes signs at each of those values. Values of x. I got a question that asks, are endpoints points of inflections? No, you do not need to test endpoints for relative maxes or points of inflections. Relative maxes and mins, points of inflections cannot occur on endpoints. However, absolute maxes and absolute mins can occur at endpoints. Any other questions on this one? I do feel like if I had to choose out of all the problems today, what might show up, I feel like this one would show up, right? Because there's not a lot of work involved. It's just a lot of analysis and a lot of proper explanation. So I hope that you know how to justify increasing, justify decreasing, justify points of inflections, justify concavity, right? And it doesn't need to be like 10 sentences. It can just be a very concise sentence. I think I'm gonna stop there in terms of questions. I'd saved one more, but I think I'll save it for next time because it's very complicated. But I want to go ahead and ask you if y'all have any questions. We've gone through a lot of the applications of derivatives this time. And as of this, we're going to stop derivatives, and tomorrow we're going to go into integrals, or we're going to start doing some basic integration as well as some applications of integration now that you know your derivative stuff. Any thoughts, any questions? We will be doing series probably next Wednesday or Thursday. I'm trying to go like sequentially through the whole calculus curriculum. So like I said, I'll be uploading the notes onto our Dropbox. I'll be putting some circuit exercises so you can get practice with some of the skills that you feel like you aren't necessarily the best at. Alrighty, if nobody has any other questions, thanks so much for showing up today. Have a good day.